Sorry that I can't. Oops. I just heard a recording and it scared me. Anyway, I'm sorry I can't be there in person. I love Barcelona, so hopefully I'll get to see you all soon in person. Anyway, so as Bruno said, the topic of this series is about infinity modular operads and the profinite Grothendieck-Teichmüller. So I'm just going to give you a little Grothendieck-Teichmüller group and sort of related groups. So the lectures will be broken into 3 parts. So the first one is about what are sort of modular operads in a pretty abstract way. Don't worry, I'm not handwriting the whole thing because I'm still bad with this technology. And it's about a sort of category of graphs that model modular operads. And the second talk will be about a model for infinity modular operads, a Siegel model, which I happen to like quite a bit, and some related structures. And the third talk will be about profinite Grothendieck-Teichmüller group and related groups. Now, so it'll start out quite abstract and get more topological as we go. I'm going to start with a very general topic and move forward. So if you like category theory, you might like the first lecture and you'll hate the third one, and if vice versa, if you hate category theory, it will get better. Also at the end of each talk, like for the first 2 at least, I have sort of set of open problems and exercises. So as Bruno said, I have a hard time with Zoom. My attention span in a regular lecture is not great, but certainly whenever I can also check my email, it's especially not great. So I put the slides on my webpage, and I'll do this before each of the talks. And I'll be writing on the slides. I'll fill them out, so there'll be more stuff. I've also put a draft, as you probably know, like we're writing lecture notes for this. I put a somewhat a draft of my lecture notes. This is probably an embarrassing draft, and there's almost certainly misspelled words in there, which you don't need to tell me about. I'm aware of it, but you can choose your own adventure. If something that I would say that the draft lecture notes are most likely full of typos. This is something that I wrote quickly for myself while I was making slides. But you're welcome to either while we go along, because it's easier if you lose track to come back if you have the slides. All right. So on that note, let's get started. So this first lecture is called Graphs and Modular Operads. This will be covering some joint work with Philip Hackney and Donald Yao. I guess the advantage to my typo-riddled draft lecture notes is all the references are already there. So that a series of 2-3 papers with Phil and Donald. And I'd like to give a special thank you to Phil for also helping me come up with some exercises and open problems for these lecture series. So we were chatting about that. And so a special thank you to my students and Sophie Rainier, who's a sort of Australia-based operads crowd who listened to earlier versions of this lecture series for a draft. All right, so what is our goal today? So I'm going to start out with a very broad definition of a modular operad and slowly refine as we go in the third lecture to something very specific. So one of the most difficult things we came across when trying to come up with a definition for an infinity modular operad was that nobody can really, the literature doesn't seem to agree on what such a definition should be. So I picked a definition here that encompasses all possible ones, and I'll show you how to specify to your favorite definition of modular operad. All right. So let's start with the notion of a C-colored cyclic operad. So I'm going to start with colored And if you're not familiar with colored objects, you can somewhat ignore this point. This is there for people who maybe are. So this is an algebraic structure like an operad, but we're going to have an involutive set of colors. So that just means that I'm going to allow that my set of colors C has an involution on it. So I want to have some sort of duality, like naturally implied in my objects. And now for every sequence of colors in C, I'm going to have my underlying sort of colored symmetric sequence. So this is a set of operations. I'm going to work in discrete, so everything is in sets for now. I'm going to have a set of operations with a symmetric group action. So I write sigma sub n for my symmetric group. Right? We're going to think about elements in here. So in operads, as you've seen, you're thinking about operations as rooted trees. So Ricardo was drawing some nice rooted trees earlier. And the main difference with cyclic operads is I don't want to acknowledge that there's a root. So I'm just going to think about an operation in here as being something that looks like C1, C2, C3, C4. Is this writing too small? Can everyone see? You can shout at me if I need to write larger. All right. And then I'm going to have a family of equivariant, associative, and unital composition operations. So we're think of, right, because I no longer have a root, I'm going to write circ ij for my operations, where I'm sort of identifying both two things that I want to glue together. So if I have one of my little spiders here, with the C1, C2, C3, C4, and I have a different one, which I'm going to call D1, D2, and D3. So if I want to if I want to compose D3 with C4, I would write 4, 3, and then I would have my resulting composition, D1, D2. I guess I have C1, C2, C3 left. Right? This is the kind of composition I'm talking about. And in the colored case, I also need to make sure that I somehow have an identification of colors. That's the main difference between colored and uncolored objects. All right. So a modular operad is going to be a cyclic operad that has a bit of a trace operation or a type of contraction, some kind of generalized trace. So a modular operad is a cyclic operad. So in particular, same thing, set of colors, my little spiders. And I'm going to add in a family of equivariant contraction operations. So in my picture that I had with C1, C2, C3, C4, right? This operation is going to be something that allows me to like contract any two edges as long as the colors match. So here is what I mean by a contraction operation. So I'm getting loops in my trees. So I'm no longer really looking at trees. I now have just general graphs. And these all satisfy some axioms. I've kind of alluded at them when I said equivariant, unital, etc., but then they also have to interact well with each other. I will put a reference in the final notes. I couldn't remember which paper I liked best. All right. So the motivating example I have in mind that we will refine more and more as we go is a modular operad of surfaces. So here, when I have my little spider, I'm going to want to think about an operation as being decorated by a Riemann surface with boundaries. Right, so here, this is going to be some Riemann surface of genus 0 with 4 boundaries, right? It's going to be an operation that I'm looking at. And then when I do my cyclic operad composition, one thing you could think about is that I'm basically gluing boundaries together. Okay, so when I choose, say, I guess these will be labels, and they can permute. I just am somehow always writing things in order, but that's artificial. All right, so when I write a 4-3 here, this composition is basically the same as constructing a little tube and gluing these guys together. All right, so my new surface has 5 of them. Here. And like I said, we'll be making this precise, especially in the last lecture, but this is just a motivation of how to think of these different gluings, right? So you're thinking of boundaries gluing together. And I guess this is sigma 0.5 over here. And the contraction operations are sitting there and they're letting you have self-gluing. So if you have your surface again, right? When I do a contraction of 2 edges, I'm creating now this loop. And what did that do, right? That's creating a bit of a donut. I have a little hole here. So now I have a surface of a higher genus. So the loops are topologically a way of going from sort of genus 0 surfaces to higher genus surfaces. That's one way to think about what's going on. All right. But I do want to emphasize that not every example, so this is the example that I'm interested in, and we're going to be spending a lot of time on this type of example. But the definition I've given you is actually like very general and contains a lot of abstract categories. So here's an exercise / example. So star autonomous categories are some kind of category with duality on the objects, closed symmetric nodal category, such that every object is its own double dual, let's say, up to something. And an exercise which actually helps you really understand this definition certainly is to show that when you have a strict star autonomous category, these are cyclic operads, for example. So this refers to a paper by Gabriel Drummond Cole and Phil Hackney. And I don't have the references in front of me, but it's one that has something like Dwyer Khan in the title. But it's worth actually trying, like looking up the definition of star autonomous category, going back to this definition and playing with it. It will give you some idea of just what's going on with the duality. So because most modular operads that people in the audience who are experts in operads are familiar with don't have involution on the objects. You can easily quotient it out. It's not like I'll show you how to do that as we go. Like I said, I'm starting with the most general thing. There's a notable exception of a paper by Pedersen that has sort of a modular operad with groupoid of colors or something like this. I forgot, it's in my notes. And then there's also just one reason for having it actually is it gives, if you're putting model category structures on stuff, there's a huge advantage to this. If you want to do homotopy theory with these things, the involutive set of colors just makes your life a little bit easier. The other advantage is that, and I'll talk about this at the end, is that you can consider things like wheeled properads as a sub-object via a slice of this type of model. So I'll leave this here. I'll get back to that at the end of the talk. It's one of my open problems. All right. So my goal for today is to introduce a category U of graphs. So this will be a category of connected, undirected. So U is for undirected graphs. and explain to you why it's basically a model for modular operads. So I'm going to give you a nerve theorem that tells me that I have an equivalence of categories between the category of colored modular operads, where I allow seat to vary, and the category of set valued pre-sheaves over U, which satisfy a Siegel condition. So all of these terms will be introduced. And so we're just going to start with graphs. So this picture I have here is my lovely graph. So as you saw from my earlier drawings, I'm not the best artist. So I have some pre-drawn pictures and some not. So my graphs are going to be, they will be connected at a certain point. This is obviously not connected. I'm going to allow for graphs to have loose ends. So they're going to be made in a way that I have loose ends or half edges, legs, meaning that I don't have to touch a vertex on both sides. And I'm going to allow for edges with no vertices. Okay, there's only one thing that I'm going to exclude, and that's going to be a loop with no edges. This guy is bad. All right, but we'll get back to him later. So I'm gonna leave that there. All right. So what is a graph? So this definition is from a paper of Joachim Koch and Andre Doyle. I think that's right. Yes, sorry. Sorry, Joachim. So I'm going to use the definition of a graph, which is sort of nice and simple. So a graph is going to be a diagram of finite sets. I'm going to have a set of vertices. And I'm going to have a set A of half edges or arcs. A is for arcs, but you can just think about a half edge as basically a copy of the open interval, right? With some kind of orientation. Now, I'm going to want to have an involution on my set of half edges that maps. I guess I won't draw the tips on the interval. That basically takes and flips the orientation of my edges, my half edges. This is going to be how I'm going to identify edges in the graph. So I have half edges and then edges. Half edges with an involution, and then T is going to be a partial map that goes from A to B. So I'm assigning half edges to vertices. And since I'm allowing that some half edges are not going to touch a vertex, I'm going to write D for the domain of this thing. So these are the half edges that touch a vertex. That are adjacent to a vertex. And this is just a subset of A. Okay, that's just a piece of the half edges there. All right, so with this example I have here, so I think if I'm going to use my technology magic, let's make it larger. Let's look at how this would work. So with the graph that I've drawn here, right, I have two vertices. I'll call this B and W. And each edge has two variables. So I'll just use random numbers as for arcs. 8, 9, 10. Okay, so my set of half edges here are just the digits 1 through 10, the numbers I've written here. So the involution I, what is this doing? This is sort of mapping, not sort of, this is precisely mapping one arc to another that makes up an edge. So I of 2 equals 1, for example, and I of 3 equals 4. And then the domain of this graph. This will be 2, 9, 3. So everything that's close to, that's touching a vertex, 4, 5, 6, and 7. Okay. Okay. So now to uncomputer magic it. Don't worry, the same graph is on the next slide. So if you're still copying numbers, it'll be there. So so just to reiterate, like the edges are the orbits of this involution. So here I had a 3 and a 4. So this edge, which we'll call E. So E is the orbit, 3 and 4 here. And this edge here, 5, 6. So this is going to be also an internal edge. Maybe I'll call it F. So this orbit here, F is an edge. So 5, this means that I takes 5 to 6, and the domain is 5 and 6 are both in the domain. They're both mapped to a vertex. So I'm going to count that as an internal edge. So the main thing I wanted to define here is that, so edges are the orbits of this involution, and internal edges are the ones that we normally think of if we're thinking about trees, but also any loop like this, right? We'll call that an internal edge. It's not part of the boundary, which is our next definition. Okay. Oh, I realize I cannot see the chat. Okay, so I have a couple of special graphs I want to introduce that have names that we're going to be using a lot of. So one is called the exceptional edge. So this edge with 0 vertices here. So you can think about this as being composed of A, and I'll write A dual. So that's supposed to be a little dagger, but I don't draw very well. So this exceptional edge is just a single edge. Right, so the set of arcs here is A and whatever this little symbol is, A dual. The domain is empty and the set of vertices is empty, right? If I want to write this combinatorially, but pictorially, it's just a line. And the other thing that I'm going to be talking about a lot is like our stars. So these are corolla, but I don't want to confuse anyone who's been thinking about trees. So we'll call them stars. And so these are vertices, so single vertex graphs, where you have 2 times n arcs or half edges. Sorry. And yeah, I don't think there's that much more to say about that. So as I mentioned, there's a couple of definitions here. So these are very important. These are the building blocks of all of our graphs. And we'll have the boundary of a graph, right, of the graph is an important thing. So I was talking about the closed loop there as being an internal edge because it's not in the boundary. So I'm going to define the boundary to be basically everything that is a half edge, which is not in the domain. So in the case of this exceptional edge here, right, the boundary of the edge is both, right, is everything. This thing. And in the case of the vertex of this 4 star, so right, we have kind of this like imaginary halfway point, and the boundary are these duals. So the boundary of the star is going to be 1, 2, 3, and 4. And the half edges, which are directly kind of adjacent, I shouldn't draw arrows, but kind of here, these we're going to call the neighborhood of a vertex. Okay, so these are directly touching the neighborhood. So in this case, the neighborhood of this vertex V is 1, 2, 3, 4. Okay, so we need these definitions to make things really precise when we start like building morphisms in our category. All right, so we do have a lot of graphs with empty boundary. So this is a loop with 2 nodes. Okay, this is a perfectly fine graph. The only thing that we're going to exclude, so like this, the boundary of this, I'll call it G, is empty. There's lots of those in our category. The only thing we're not going to allow is this nodeless loop. So if you wanted to write this in our formalism, right, it would have the same presentation as our exceptional edge, but it's not equal to the edge. So we don't really want to think about it. So what we're going to do is we're going to just get rid of it, right? There are ways to deal with, there are lots of different ways to deal with this. We have an extension of this category in which you include the loop, etc. It's a subtle point, but just pretend it doesn't exist. All right. So I left one of an exercise, which you can see. So I just gave one here, and I'll leave it in the notes where you can draw a graph. So this is not a unique answer, but there's lots of answers for this, where you have A and D and B. So I didn't give you T, so it's not unique. But you'll find that this is a graph with empty boundary here. So it's my hint. The boundary of G is empty, right? And sort of going on with that that exercise, there's some important features of graphs that we'll think about, like from the boundary, you can create a vertex that's, oh, yep.
We have a question on the chat.
We don't allow empty graphs, no. I guess all empty sets is no. I mean, I guess you could. Yeah, no, it's not connected, so I haven't thrown everything out yet, but no empty graphs. I do allow, and that's actually part of the exercise here, like a single vertex. It's just like hanging out, and that's in fact what the star of G from the previous graph will look like, as an empty vertex. That, yeah. So the star of a graph would be if you take the boundary and then just like create a corolla out of it. And the star of a vertex, again, is going to be like a graph made out of a vertex. And we're going to see examples of that as we go. So these are both important. And if you play with that exercise before, so if you get lost later in the talk, you can come back and do this exercise. So at least learn how to do the graph part. All right. Okay, so the objects of my category U are going to be connected graphs. So the objects of this category U are going to be the connected versions that I just talked about with all that combinatorial data. The difficult part of the category U is to describe morphisms. So we're going to use a particular kind of morphism that basically explodes vertices in a way that reflects modular operad compositions. Now, to arrive at this definition, we're going to do some funny things. If you haven't seen this stuff before, if you have seen this stuff before, it won't be completely excited. There are various other definitions you could have used, but this will allow you to avoid things like duplication of variables and sticking with the idea of operads that basically, right, if you, in general, in operads, they only model algebras in which you can't duplicate variables. So that's one of the reasons this definition is a bit cumbersome. So I'm going to give you a first part. So embeddings are one class of our graphs, and they're the nice ones that make sense and are easy to describe. So you could think about graphs as basically just diagrams in the category of finite sets in the shape this category I. So here by diagram, which I think is maybe these days an outdated term. I mean, categories in the, or objects in the functor category. I don't know if it is or not. I feel old when I say it. In which you take, you know, this map to be an injective and this thing to be an involution. The endomorphism I should go to an involution. So it's a graphs are subcategory of finite sets in the shape. So I'm going to define one notion of an embedding. So this will be a natural transformation of diagrams. And we're going to require that I have that this right-hand square is a pullback. So this assures that local information around each vertex is preserved. And in fact, I'm going to call it an embedding where I have, this is a monomorphism. So I want like an injection on vertices, and I want, if there's like 4 things attached to a vertex, it goes to 4 things attached to a vertex. So note, by making this a pullback, this is also an injection. Yeah. So this is one type of thing as an embedding. You don't have to have an embedding on arcs. Okay, so the biggest class of things that we'll see a lot of are things called vertex embeddings or star embeddings, where I can map the star of a vertex into G. So let me draw a picture. We'll see how well this looks. All right, so this is G, and this is V, and this is W. Then the star of V, so remember, I went kind of fast, but I take the neighborhood of V and I make a star out of it. So we'll call V, and then I have this thing here. Right? There's going to be an embedding here where I have an injection of vertex, and oh, I added an extra thing just to like mess with everyone, including me, and precisely 3 things attached to it. So non-example at first. And then embeddings don't need to be injective on arcs. So here, where I take the neighborhood of this W, so this is a little spider with 5 legs, they map here, right? And you can make this really precise in terms of that diagram, which I put here. So, right, you map the vertex into the set of vertices, the neighborhood of V into D. These are natural injections. And then here is the map of arcs given by the neighborhood and the neighborhood dual, when you add the duals to get this the star of V construction. Okay. But this doesn't need to be injective on half edges. So you can have something like this, and I'll just draw a few things. So, right, if I'm thinking about this as being like one dual, two dual, and I don't know, this will be 3, 4 dual. Right, if I'm mapping this star here into here, so what do I have? I have a map from V to V, that's injective. And right, the domain is the same. Nothing has changed, 1, 2, 3, 4, 5. I mean, it's even the identity. And now here, what am I doing? I'm just, the only thing that's not injective is I'm taking 1 dual to 2 and 2 dual to 1. Right, that's the only thing that's not the identity, which is on the set of arcs. So this can tell you a bit about what a graphical morphism is going to look like in general. So embeddings are a class of graphical morphisms. They're really nice ones. But in general, what is it going to consist of? So we have the data, a map of the arcs, so the half edges. Sorry. I like told myself I'd call them half edges, and I wrote in my paper arcs, and somehow I cannot get it out of my head. So half edges. And also then there's data about the local area of V, right? So I have the vertex where it goes, and sort of, oh, that's not the thing I wanted. And I'm basically also giving you the data about this local area of V, as well as data about the morphism. So I'm going to give you a big scary definition and then draw some pictures and hopefully claim it's not that scary.
Can I ask you a question?
Right.
A quick
Of
one.
course.
I remember the definition of a graph after, you know that people were using, I guess, like Abramoff, Manin, Borisov, etc. And for them, they had a set of half edges with involution, a set of vertices. So it's not the definition of Joachim and Andre. Here, what you have is when you have a leg, see, you need two half edges to produce, say, a leg. You see a place where you need to plug something. So here, for in this definition, you need two half edges to produce a leg, and for them, they were using only one half edge to produce a leg. So why is it better or good for this new definition?
So it's not really, I mean, so you can pick any formalism you want. So one reason is that, I mean, I can tell you the reason we use this one is because this was the one that already existed in the literature in something closely related to what we wanted to do. There's a slight advantage that if you want, we really want to talk about neighborhoods of the vertices in this definition of graphical map. It's quite important. And then boundaries. So it's a way just to make graph substitution kind of formal. But as you know, in previous work I've done, I haven't used this language, and you can still make graph substitution formal. So, and I should have said this at the beginning, you can choose your own graphical formalism, and as long as you can make this definition of maps work, of which, to my knowledge, all of the formalisms I'm aware of work the same, and you can. They'll all work with this. So if you have your favorite definition of graph, like the one from Getzer-Caprano, this definition will still make sense, and it might even be easier to write down. Well, no, they're about the same.
This is undirected, yes. I think she can hear you, the microphone.
I think I can. No, I didn't hear whoever asked that question.
Yeah, yeah.
Okay.
Okay.
If it comes back, we'll come. I heard something, but not the whole question. So great. So the definition of a graphical map from G to G prime. So I'm just going to have a map on the half edges. So, okay, there's questions in the chat. One is there any advantage of this definition? It's short. So when you're giving a talk, it takes a lot less time to write down. It's just like one line. I guess that's one. In practice, it's actually not how I think about graphs. I tend to use a very laborsome definition because I like having all the data. And then Emma, I actually don't know the answer to your question off the top of my head because I don't remember Manin's definition. Not like but perhaps if Joachim is in the audience, he might know. And Sophie might know who's in the audience. But I don't remember Manin's definition off the top of my head, but I think they're all formally equivalent. So mostly there's this great paper by, there's this paper by Berger and Patanin where where they show that basically all formal graphs are the same. I don't know. It's the one that has tame polynomial monads in it, and I'll put the reference in the final notes. And I don't know if it includes Manin's definition. Okay, and so yeah, it's you can pick, but mostly it's because it's short. That's going on here. So Right, so we have a map. So what is a graphical map going to be? It's going to be a map of half edges. And then I'm going to give a function, which we'll call piece of 1, which basically takes at each vertex, it's going to assign an embedding. So what do I mean? I mean, basically at each vertex, I'm going to give you some other graph. So this is some other graph, which we'll call HV, and an embedding of that graph via phi1 at V into G prime. So in other words, at each, this is, and I'll draw a picture which will help hopefully make this clear. At each vertex, I'm going to blow it up into a subgraph. Oh, thank you, Clemens. I'm going to blow it up into a subgraph and of G prime. Okay. So then I'm going to require a couple of conditions. So I'll come back to each of them. Again, they're not that scary, but the first two just mean that what I said makes sense. So I don't want anytime I blow up a vertex with a subgraph, I don't want there to be any overlap of vertices. So I really want that to be like uniquely considered. And then I also want there to be a sort of canonical definition between the neighborhood of a vertex V and the boundary of this subgraph. So here I'm talking, this means like some graph V, and there's a picture on the next slide I'll explain. This third condition is just about how we hate this loop. We hate loop. Right, so this is a non-collapse condition. It's just so that you never have a graphical map that allows you to fall out of your category, okay? Now, let me give you a picture so that this doesn't look as bad, all right? So here's a G, and here's a G prime, and I'll call this V, and I'll call this W. And so what happens here? So at V, see, I have my neighborhood of V. I'm going to assign to V an embedding into the star. Okay, so I will say that, so if this is phi, then what happens here is that phi1 of V is an embedding of basically the star at V, which has 1, 2, 3, 4, 5 guys, into the contracted corolla, the contracted star here. 1, 2, like that. Okay. And the second one at W, so this is a more interesting thing that I've blown up. So W, well, this got blown up into this whole graph. And see the boundary, the embedding here is, oh, you know what, I didn't actually test this out, but maybe I can do it. The embedding here is, nope, that's only going to copy what my little purples. Is this whole subgraph is embedded into here. So this is like this whole graph is embedded in. So we can call this guy H, B, and phi1 of W is the embedding of this here. Okay, so again, that's basically, this is a way of saying that my graphs are given by either embeddings, my graph morphisms are either given by embeddings or graph substitution into the vertex. So, so either embeddings, oops, or graph substitution. So I am blowing up a vertex. Now, this is a very complicated definition, but luckily there are there are 3 elementary graphs. So every graphical morphism, every morphism that I've just described is a composite of some elementary maps. Sort of some elementary maps and isomorphisms. Okay. So, so here is my initial graph G. And I'm going to say that an inner coface map, okay, which I'll write as D sub V because it's determined at a single vertex. This is going to be a graphical map that blows up a vertex V in G and it adds precisely one internal edge. So in this case, didn't label my vertices, but this guy's V, okay? And I'm saying that I blow up V by adding in this vertex, this little graph here. And this guy is here, right? So I blew up V, I added this new internal edge. So that's my new internal edge. And if you're familiar with like dendroidal sets, this might be kind of familiar to you. The only difference is that we can also add weird loopy internal edges. I think I hear a question. No? Okay. So I can also do something like this where I have my V and I can have, oh, this is bad. D1, so it's dV1 of V. Yeesh. This would be dV sub 1 of V, which is not great. We'll leave this last part off. So I've substituted in now this like contracted corolla here and here. So I added, this is my new internal edge, this loop. Okay. My second class of elementary graphs is going to be outer coface maps, and these are embeddings. So these are either, there are 2 types of embeddings that will count as outer coface. So one, I'll write DE because I'm adding an edge, is an embedding from G to G prime, where we gain an internal edge. So you've already seen this when I talked about embedding a star into a contracted star. So here, right, this is, we have this identity, oops, sorry about that jump. I have this identity on everything except for here. So this is my new internal edge on this embedding. And the other type, well, is just where I map an edge onto some internal edge, right? So I have an embedding in that direction. Okay. And finally, codegeneracy maps. So these are maps that blow up a vertex by an edge. So they basically just kill a vertex. So in this case here, I have this vertex, and I have substituted in an edge there, and I've killed it off, right? So note that condition 3 of graphical maps says the only one that we don't have is this guy, right? This is not, this is literally the reason for that. Oh, this second map, sorry, I missed it. You mean the edge here? Yeah, so this is just, you can map, I'm just gonna say that I have a map from the single edge into the star of V. So, right, I have, it's sort of trivially true. So you have the edge, I have to draw my diagram. So I have this set. If I want to draw this in a diagram, right? And I have empty, sorry, it goes that way, empty. And then I have whatever, I have my one star, n star. This is like 1 through n. And this is B, right? I have this diagram here as my embedding edge. There. So this is the thing. Right. So I'm taking, I guess, that the empty set includes into everything. Great. Okay. So we were here. Yeah. Okay. So the graphical category now. So just U is, to summarize, the category whose objects are the connected graphs, and the morphisms are the graphical maps. And it's perfectly fine for you just to think about them as being generated by those 3 classes of maps. All right. So I claimed that this category was really closely related to modular operads. And in fact, we're going to explain that a bit. So in fact, it's you can freely generate a modular operad from any graph. So this somewhat bad notation is because you run out of symbols sometimes. It doesn't have any really special meaning. So I'll just say that the modular operad, you can generate a modular operad from a graph. And well, how do you do this? So here's my graph G. And it has a bunch of colors. So I'll just label A3, A4, A5, A6, A7, just to make this a bit smaller. And I'll assume that the duals are all there, if that's okay. Where here I meant like AI equals AI dual. Just to make my notation a little bit better, or maybe worse, depending on your opinion on that. So the set of colors of my graph, my modular operad, is going to be the set of all the, oh, that's not the highlighter, the set of all the half edges, A. All right, so remember we had to have an involutive set of colors for our modular operad. So in this case, right, A is A1 dual, and so on. Right, that's our set of colors. So it's already got an involution. And now I can define an underlying collection or symmetric sequence, just called it E. So, which is basically defined as taking the boundary of a vertex in V. So in this case, so with what I've drawn here, I'll write E at sort of A1 dual, A2 dual, A3 dual. I guess we'll decide that A5 and A4 are adjacent to W. And the value of this sequence, well, this is just going to be V, right? And similarly, if I take this with E and I take now, this will be A4 dual, A5 dual, A6 disappeared, and A7 dual, that this is going to be the set W. Okay, so, and then there's no other elements in my symmetric sequence. And then I'm going to take the free modular operad on that. So note that these not just V and W, like I have all the different ways of pasting it together. So you think of the corolla as like the building blocks of my, so composition is given by iterated graph substitution. Yeah, I'll go back and draw that at the end if I have time, but it's just, you just iterate the substitution, but I'll go back and draw that at the end so that we don't lose too much track. Sorry for everyone. In the chat, there was a question about how you compose morphisms in U. All right, so Right, and so you think of the corolla as the building blocks, and then the graph gives you some pasting operations. Okay, so this is a modular operad. So I don't remember which paper I called 2 and which one I called 1, but there's a proposition here which says that the assignment from a graph to the this modular operad, this gives me a faithful functor from the category U into the category of modular operads, which is injective on isomorphism classes of objects. So this is not a full functor, and this is something you see as soon as you leave the notion of simply connected graphs a lot, like with properads or wheel properads or any of these things. And here's a counterexample. So if I, and I think this example was first shown to Phil and I by Joachim in the context of giving an example of a tau map that's not an embedding. I think that's correct. So sorry if I'm misattributing that. Apologize. But here, I'm going to let this graph G and the modular operads, there is a map of modular operads from G to G prime. So if this one is G and G prime, where you send basically the operations generated by V1 and V2 to V, and the operations generated by W1 and W2 to W, but there is not a graphical map. This is something that we've eliminated, map G to G prime. Right, so it's not a full functor, but it is faithful. This falls under the category of when you leave simply connected graphs, you get some weird stuff. All right. Now, to make it a bit more clean, what the definition or the connection between graphical sets and modular operads is, between U and modular operads, I'm going to introduce the notion of graphical sets. So we know that U is related to modular operads, but we can in fact make a closer distinction here. So I'm going to introduce the notion of category of graphical sets. So we don't call it this in our paper. I was just thinking that many members of the audience will be familiar with dendroidal sets. So this might invoke something in your brain. So this is the category of set valued presheaves of U. So what I mean by that is a functor from the opposite category of U into the category of sets. And we're going to write X sub G for the evaluation of X in a G. So you think about this as being right, the set of, I always like to think about this as a little bit of like decorations of a graph by some little elements in X. And so it's a set of all possible decorations of this graph. This is not the worst way to think about it. And because it's a functor from the opposite category, note that from any graphical map, you get the opposite one. So X from G prime to G. So this is going to look a little bit more like modular operad compositions, because instead of blowing up vertices, I'm like contracting edges. And we'll have a special definition here of a representable graphical set, graphical presheaf at G. All right, so this has a special notation with the square brackets. So U of G, it's supposed to remind you of like the representable simplicial thing or the similar thing in the dendroidal case. So this is the functor of maps into G, and I don't know why there's a semicolon there. It's just supposed to be a comma, so sorry about that. Where I take here the maps at any H, at any other graph, U of G at H is literally the set of maps from H into G, right? So this might be empty lots of times, but it's otherwise just the set of all subgraphs there. Okay. So I want to look at special maps in this pre-sheaf category called Siegel maps that will mimic the notion of a modular operad compositions. And then when I impose a relation that the Siegel maps are strict or bijections, then I have my equivalence that I promised at the beginning of this thing. So you're going to want, so there's a question in the chat about if in the definition of modular operads, we compose operations about inputs of identical colors, but in the free modular operad, we compose along inputs of dual colors. And so yeah, I had that you have something like PC1 DN times PD1 DM goes to this thing. And I think there was like a DJ and like that. And I did say CI equals DJ. So you are correct. There should be like a dual there on one of these. So you want them to agree in sort of an involutive way. So there should be a thing there in the composition if you're going to have this involution on it. Thanks. Thanks for that. And also, if any of my students are in here, remind me to fix that in the notes, please. All right. So where were we? Oh, right. So I was going to talk, I want to talk to you about Siegel maps. And so the notion here is that I want, these are going to be maps in this now pre-sheaf category. So these are maps in set U op that model, that like really closely resemble modular operad composition. Okay. So I'm going to build this up by thinking about internal edges and how the internal edges are supposed to be like compositions in our operad. And I'm going to introduce this with some weird limit. Okay, and I'm going to explain to you how it works. So for any internal edge, so an edge that's connecting V and W, right? I'm going to have inclusions. I'm going to have embeddings that go in each direction, right? So if I have an internal edge between V and W, and in this case, remember V and W aren't necessarily distinct. I have a diagram like this from internal edges. And I'm going to introduce this thing. I think we call it a corolla ribbon, or some people called it a necklace or a corolla necklace or something, but it's just a limit over the diagram of all such maps. And when you first see this, it might look a little bit weird. So I want to actually like do one. I want to give you an example of how this works. So let's see, we'll call this, I seem to be really on B and W today for this graph G. And now it has three internal edges. We'll call this E1, E2, and E3. And so I can build a bit of a diagram. I'll have I don't know why we started with 3. We'll have E1, E2, and E3. And over here we'll have V, and here's W. So, right, I have this diagram from E1. Oh, I should write the star. It's really a star, right? So if you hopefully can imagine enough that this is actually a line. So from E1, I'll have a map into V, and I've got a map into W. From E2, I have a map into V, and I've got a map into W. And for E3, I have now 2 maps into W. So if I apply my pre-sheaf and everything goes opposite, so I'll throw an X on here, and I flip my arrows around. Right, we got an X, X, X. Now, this is the thing I'm going to take the limit of. So X1, oh, sorry, X sub G of 1, well, this is the limit of this diagram. So this is a limit in sets, right? It's nothing too difficult for you to try, and I would recommend. So what is this, right? This is going to be the product of X, the star V, X star W, and then you have some relation given by these identifications. So you're going to have some quotient there. And I'll let you play with that for a second. But it's a fact that that limit, right? So it sits inside the product, and all the star embeddings induce what we call the Siegel map. So one way to think about the Siegel map, and there's another way we'll talk about tomorrow with Siegel cores, I just want you to see both in the same series, is that you have a map from the evaluation at the graph G to the product of the vertices. So you're thinking about somehow the decoration of the full graph. I don't know what's here. This guy, right down, I should add an extra one, to the data here of whatever you're decorating these by. And what are you getting? You're actually getting along the composition of the 2 edges, right? So you sort of really have a picture of that this looks like composition. And so this is going to factor through this corolla ribbon. And it's one of the exercises that I think this is not so bad. This is a limit in sets. If you take the evaluation at the exceptional edge is always a point, then this is just equal to the product in sets, right? So it's not so bad. So in fact, then you have, if you take this to be one colored, basically, you take the X to be a single point, then you have a map from the evaluation into the product of the vertices, which is exactly what you would expect in a modular operad map. Great. So a graphical set, right, will be strictly Siegel if the Siegel map is a bijection for every G and U, right? So thinking about what this means again, I seem to constantly draw the same graph, so I'm going to try to draw a different one. Make it a loop. So I have some values on here, right? I'm thinking about this as living in, so I have some X1, X2, and I'm composed along some internal edge E. And now I have some little spider here. This part's like E hanging out. I have X1, and I have here, I have my E, and then this is my X2. And I'm saying, what am I saying? I'm saying that when I compose these 2 objects along E, right, that I have precisely this. So if you go this way, right, this is the map of, this is the sort of composition in our modular operand. This is the way to think about what's happening here. Okay. And in fact, we can make that precise via the notion of the nerve functor. So given a modular operad P, I can define a functor from modular operads to graphical sets, where you take the nerve of a modular operad, so at any G, and that's just going to be the map, the set maps of modular operads from this freely generated guy by G into P, right? So for any P, and any G, and oh wait, okay, the rest of the stuff, I thought there was more stuff on that slide, and it turns out I just had to scroll. Okay, so right, what are we saying is that the nerve, this pre-sheaf here, NP, is the set of P decorations of G, right? So at the exceptional edge, right, the modular operad maps from this edge to P. This is this involutive set C. This is the colors. This is the colors of P. Sorry, if that's not clear where the C came from. And now I'm saying that, well, at any particular star, that when I look at the set of modular operad maps, well, what am I going to get? I get this set here, because what am I looking at? I'm looking at C1, C2, C3, C4, and I'm looking at all possible little P decorations of this graph, right? So it's literally the set of the operations in P from C1 to Cn. So I'm assuming here that that the star has C1 through Cn around the edges. Maybe I should say that. So the star has C1, C2. All right, great. And so, oh, this statement is weird. Okay, so there's the fact that the nerve functor is fully faithful. All right, and in fact, the following are equivalent. This sort of reads a bit weird. For a modular operad P, or X is, maybe I should say, proofreading in real time is always great, I think. So there exists an isomorphism X and to the nerve of P for some modular operad P. And then X satisfies a strict Siegel condition. So I'm saying these are equivalent. In other words, right, this is an equivalence of categories. And I wanted to mention here, so that there's a different category, sort of introduced by Joy Koch. And then there's a Feynman graph, so it has slightly more morphisms than this one. And Sophie Rainier has in her thesis, and there's a paper on the archive, a similar theorem, a nerve theorem like this. So it has a nerve that's fully faithful from modular operads to graphical pre-sheaves that satisfy a Siegel condition. It uses this Weber nerve. Is it 1B or 2? Is anyone proofreading? And maybe, anyway, it uses the Weber nerve, so a more general thing. So there's another fully faithful nerve. If you want some extra morphisms in your category. And sorry, Sophia, I didn't write down the name of your paper, but I'll put the link in later. All right. So so this nerve is fully faithful, and we have this equivalence at the essential image, right? So what does that say? That's basically saying that we have an equivalence of categories between modular operads via this nerve with the set of pre-sheaves U that are strictly Siegel, right? So the point I want to make with this, as we'll go tomorrow, is that you can, so if you want to think about a modular operad, right? So if we want to think about a modular operad, we can think of it in a very formal way as a pre-sheaf over U. And what we're going to do in tomorrow's lecture, right, is we're going to want to relax this so that our Siegel condition is a bit weaker. And then we can say that we can argue that that's actually a good definition of a modular operad whose composition is up to coherent homotopy. And that's for the weak Siegel. Okay, so I think, oh, okay, I did give a weird exercise. So this is sort of the end of the new content. I have a slightly, oh, thanks, Sophie, I appreciate it. I actually meant to write it down. I think it's in the draft notes. So this is the end of the main content. So if you really want to get your head around these graphs, and if you haven't played with the non-simply connected case, I think this exercise is a pretty good one to do. And so we have now two ways of getting an object, of getting a modular operad. We have two ways for any graph to think about a set valued presheaf, a graphical set, right? So one is the representable presheaf, which is, again, if you forget, right? These just maps from H into G. And the other one is taking the nerve, right? So first freely generate a modular operad and then take the nerve. Okay, so this representable is actually smaller, so it's going to be a sub-object. This comes from the fact that this functor is faithful, but they're almost never the same, right? So my favorite counterexample is just pick any of these loops with nodes. They tend to break everything, and they're also very small, so they're a good example to check. But you can check any graph you like, and you'll see that the presheaf, the representable, sits inside of this nerve. Like it's not equal. But if you have, there are some cases where they coincide. And so this star sub 0, this is the thing that it's just a vertex, right? Yeah. So this guy's the same. And this is worth playing with if you haven't encountered these, any of the graphs out of the simply connected case. If you're familiar with dendroidal stuff, it's a little bit nicer. The second you start adding more structure, things tend to break a bit. So this is a place where you might get comfortable with this behavior. All right, so I promised some extra problems. So let me just say this. So stuff that I didn't mention that people might be expecting. So there's a notion of inner and outer coface maps, right, of the graphical set. So you could, in fact, define a horn, which is the sub-object of the representable. And you could define an inner con condition. So you'd say that you have a strict inner con graphical set, which is a presheaf, such that every one of these diagrams admits a unique filler. So this unique corresponds to strict. And so my student Michelle, and her thesis is on my webpage if you want to see this part, show that this is equivalent as well. So this nerve functor from the modular operads to simplicial sets to set valued presheaves, which are strict inner con, those are also isomorphic. So if you like quasi modular operads, that you can play with that too. But we don't have a model category structure on the category of graphical sets for where you would have the fibrant objects, the weak inner con graphical sets. Oops. There's not really a reason for this, just somehow it never came up that we've attracted. And I've checked, and I don't think anyone I know is working on it. So if somebody is working on this, please let me know so I stop giving your problem away. But because these graphical categories are somehow like with this involution, So graphical categories for cyclic operads, wheeled operads, etc., can all be derived from you. These star autonomous categories, they're either subcategories or slices. Having such a thing would be a really nice way to model lots and lots of different infinity operads. So that's my open problem for someone to, and if someone, of course, is working on it and needs help, you're welcome to reach out to me or Phil or Donald. We're always happy to talk to people. All right, so I will stop there and make an extra page so that people can ask me questions. So I guess I'm a little bit short. I can go longer tomorrow. All right, thanks.
We have time. Thank you very much.
Oh, I had a question about composition, but I'll let some other ones come in and then I'll write this one.
Okay. Is there any question in the audience? We have a microphone which works. I think your lecture.
It sounds great. I can hear it, Bruno.
Good.
And if I completely relax set up without any seagulls, I don't know exactly what you're saying. So it's just a category, it's just a pre-sheaf category without any seagulls. I guess I don't know if it has a word operatically, like what it means if you relax that. It's just it does have like these graphical maps look a lot like compositions, right? So given a graph like this, and then you like, so I'm gonna just go ahead and draw it. Oh, I should have gone the other way. So I'm going to draw this in the opposite category so that it looks like more like composition, right? So if I like collapsed this edge down, so this is this would be, I guess we'll call this G prime and this G. So if I have like, nope, I just primed two things. So if I have something like this, like it looks like an operad, but I don't have like a name for that thing. If I don't enforce it to be a bijection or some kind of up to homotopy thing. I think that was your question. If I misunderstood you, please feel free to ask me a different way.
You can hear me, Marcy?
Yeah, I can hear you.
Can we add the condition on star autonomous categories to get modular operads, a modular operads?
So conjecturally, I think it's like for these like star autonomous things. I hope I'm understanding correctly. Sorry if I'm not. So so you want them to be strict. So I require like everything to be like a strict symmetric monoidal. I expect it's true for week 2, but I don't know how to prove it. And by that, I mean, I haven't really tried. But I think it's true. And I would very much expect that to be true. Like even if you have just a general star autonomous category, it would work. And then I don't know what the star autonomous categories with trace, or those called like compact closed. Sophie's nodding and she's at Macquarie, so I believe her. So compact closed categories would also be examples. And I've only checked this stuff for strict ones, but I'm pretty sure it holds quite generally, but that's conjectural, I guess, because I have never seen it in the literature, but that should be a example. So I should.
Could we think of morphism from a modular operad to this kind of modular operad as algebras over the first modular operad?
Yes, you definitely. So yeah, you mean like you have some like a modular operad to some. I'll just write star cat like this thing. You could think of that as as an algebra over the modular operad.
Okay.
Yeah, because it would impose some structure on it. I guess this is most like cyclic. And this is, sorry, these are more like cyclic, and these have the trace. So I guess it would be cyclic. Yeah, you could definitely do that, right? Because it's just like if you have a map from an operad into another operad, you can count part of it as an algebra over that operad. It's the same kind of thing you could play via restriction.
Okay, thank you.
Does that make sense, or should I write that down? Sorry, but yeah.
Also a small question. Can you actually embed dendroidal sets into graphical sets?
You can. It's a bit of a workout. So I'll do this at the end of the next one. But so you've got simply connected U.
Yeah.
And then you'll have something that we'll call U-sic, and you have a map here. You have a dendroidal sets, so it goes this way. Yeah. In fact, you actually have an adjunction. I get confused sometimes. You actually have dendroidal sets, and I'm not going to draw arrows just yet. I'm really bad with ops, especially on the fly. And I guess you don't know which one is left and which one is right. There's in fact an equivalent adjunction here, and not an equivalence, and also simplicity. That's actually one of my open problems for the next, at the end of the next lecture, is like, what kind of relations do you need to put on generalized Reedy categories to like make these nice equivalent adjunctions between all the different graphical categories. But there is an adjunction here. We don't have it written down in our paper, which I noticed when we were writing it, when I was writing these talks, that somehow that was really like a huge oversight. We do have an adjunction between something that we called this like a different version of cyclic C, and then we have an adjunction there between dendroidal sets there, and this factors. This is a commutative diagram, sorry. So it's not written down directly, but I will write it at the end of the next lecture. That was my plan. So I don't know why we didn't. It's just not there. I was a bit surprised. But yeah.
Great.
You have a question on the chat. Will you make available your notes?
Yeah, so there's a spot on the webpage for the filled in slides. So I'll put the ones that I drew on up there, and then the next, I'll do it right after this while I'm multitasking during Geoffroy's talk. And then, then the second lecture, I'll do the same thing, because I find slides, I get a little bit confusing. I find slides confusing. So, but since I can't leave my island, it's the best I could do.
It's very much appreciated. It was very clear, and the slides are very clear. So thank you very much, Marcy. Is there any
Thank
question?
you.
I mean it. Is there any question on the chat online in Japan? Right?
I had my question about the composition.
Oh, yes, sorry.
Yeah,
so
just to be more precise, it wasn't so much about what happens with the graphs, because I think in terms of pictures, it's clear to at least me what is going on. But I was, in particular, I think, wondering about what was happening in terms of these maps you use to define the morphisms. Say, I mean, these embeddings that you have from V to M G prime, if you have some such phi1, as you call it, from V prime to M G double prime, how do you produce the composite embeddings?
yeah, okay, so that's actually quite a task, because what I've kind of been brushing under the rug is in particular that, right, embeddings, there's like an infinite class of them, because they can always change, but well, in like, once you have loops, you have weird kinds of things happening. So the answer to that is it's too hard for me to write down quickly in a talk. Unfortunately, it's really easy to draw a picture of graph composites. But yeah, I can write you a little something, but yeah, we wrote it down carefully. When you do the composite of embeddings, then you have to account for all the possible isomorphisms. So it takes a little bit of, unfortunately, finesse to do that. Yeah.
Okay, but do you have a reference why you do it properly, maybe?
Yes, so I do have a reference. So this one is a paper, and since I've already given my website thing, it's called, which one is this one? It's called A Graphical Category for Higher Modular Operads, and I can find the exact reference later. Clemens, yes, so there is a factorization system in U as well, just like omega. So it's a Reedy category, it's a generalized Reedy category. We also have, I think we do several different things. So you have a weak factorization system and also like a orthogonal. It's much nicer than a weak factorization system. I think it's orthogonal. Not I think, it's orthogonal. So yeah, you have all these different factorization systems. I think that is also in the graphical, what I call the first paper, the graphical categories. It's called a graphical category or something. Yes, also active inert factorization. Yes, the active maps are the ones that sort of behave well on the boundary. Yeah. And that's also written down in there. So, okay.
Is there any other question here or anywhere else in the world? Okay. So let's enjoy some coffee. Thank you once again, Marcy. And I'm sure.
Thank you. Great. And now I get to relax and harass Geoffroy next. So let's go.
We'll resume in 26 minutes at 11 a.m. here at Barcelona time. Thank you.
Thank you. Bye.